Oh, he brought water.
All right.
Awesome.
Let's see.
Just put it to play immediately.
Okay.
Thank you. It's so good to be back on this stage and back in Dornbirn. It's a very amazing conference with amazing people, amazing speakers. So Rareș and I today have prepared a... Wait, where's Rareș? Has anyone seen Rareș? Okay, hopefully he shows up soon. So we're going to start with a small demo application, just to show you what we'll be talking about today. So I prepared this small application called Coffee Application because we all love to drink coffee so much. And I'm just going to build it quickly so I can serve it and show it to you. Since everyone has been working on bundlers and compilers these days, I thought I'm going to give it a go as well. It's not using Rust like everyone else, but it's using top-of-the-line hashing algorithm that, as you can see, first gets your timestamp and then finds the first prime number based on this timestamp, and then uses this prime number to feed it to ChatGPT to ask what is the word in this number in the War and Peace book by Tolstoy. And finally, with this information, we can hash our files. And since building or bundling application is a very special moment in everybody's life, we wanted to make it memorable. So we also asked Midjourney to generate a unique memento for you, so you can always come back to that photo and remember this amazing time when you built that application at that moment. So, okay, it should be done now soon, I guess. Just a little bit more. How are you all doing? How do you all feel?
Sorry.
Hey, Rareș, where did you go?
I knew you were going to build an app, so I got you some coffee.
Oh, thank you. So
so we can drink something while watching the build.
We can wait, yeah.
We can take a break now.
Thank you. Maybe a Lungo would be better, but thanks anyways.
Okay, it finished?
Yeah. Okay, so I guess this happens to a lot of you, that some processes just take too long, and then you kind of fade away and lose your focus. And who knows what is the easiest way to procrastinate? Spoiler alert, it's none of these folks, though. Depending on your personal preference, they could snatch a big portion of your time. Now, it's actually those processes that we keep running that kind of then stop and we have to wait for them. This is what takes our focus away, and then we usually think about, maybe I want to Google for this or that, or you go for a coffee break. Even if you already had coffee like 15 minutes ago, you go for another one just because you can. And although we keep blaming our tools, and tools keep getting better and better, and now we're switching our JavaScript to Rust to make it even more faster. And again, they're still slow, but it's not the tools that are slow, it's our architecture. It's always our architecture. So maybe instead of trying to push those tools to be crazy fast, maybe let's look at our architectures and what we can do about it. So today we're going to share a couple of tricks, how you can speed up your architecture, and to narrow this window of opportunity where you can kind of snooze away. But before that, let's just introduce quickly. I'm Miro. I come from Vienna.
And hi, everyone. I'm Rareș. Hope you can hear me okay. If not, I'll scream a bit louder. And I live in Scotland. And yeah, we both work for NX. So NX is a build tool. It's also a task orchestrator. And we're going to talk today about some of the mental models that it introduces. Okay, cool. Oh, who needs sleep? No, sleep is important. So let's talk through how we build a specialty coffee delivery app. Right? So we can start out with just a single app, right? We can think of it as like a single unit in there. But from that, really, all the business logic resides in those three screens. So you might have a screen for selecting the origin of your coffee, right, depending on what preferences you have, a screen for customizing the grind size based on your preferred brew method, and of course a screen for paying for your order. Right? So our app becomes this really thin shell, and that's how we're going to think about it, that just lazily imports all these features where all the business logic lies. And we might extract some more from there. Right? So you might have some generic coffee components, right? The chakra UI of coffee in there. You might have a service for doing payments. So we're already starting to think of our app in terms of these modules, similar to NPM, right? So some of these could be deployed to NPM later on, should you want to. And we can extract some even more generic code from there. So we might have some utilities for making HTTP calls, some utilities for interacting with Stripe. And all of these modules, you can think of them as just folders. Folders that we've created outside of our main Coffee app that is then assembling everything together. All of these folders are depending on one another, same as your node modules will start forming a dependency graph as well. But because of, and it's nice to think of your code in terms of these logical units, right? It has structure, it makes sense, encapsulation is always nice. But because we're now thinking of our code in terms of these modules that are separate in their separate folders, same as you would create an open source library, you can add some just configs in there. And because we've added those, we can now individually test each library. So if I'm just working on changing my HTTP utilities, I can just rerun the tests for those, rather than testing my whole source code tree. We can even add some tsconfig in there. And we can build our library, we can build it locally to our node modules, so that other libraries above can use it. So now we have all these separate tests. We can lint each individual library rather than linting all of our code each time. And we can even build them separately. And we might even have some end-to-end tests that serve our app and test it. But we'll come back to that later. And now, if I'm just working on the grind side screen, if I'm just making changes on there, well, I will have to build my Coffee components first, right? I'll have to build them, generate some bundles into my node modules. But once they're built once, they're not going to change that often. So I can just keep changing my grind side screen, and I'll reuse that same build that I did once. If I switch branches and I build something for my Coffee origin screen, it still uses that same, I can still use that same build I did 2 days ago. So I can keep changing those without having to pass all of my Coffee components each time through my Webpack TypeScript loaders.
Okay, this sounds cool. I mean, I like how you split everything, but when I look at this graph, like, how do you know how these things are connected? This all feels like it's full of some magic that only you as a maintainer may know. So what if I'm a new team member and I just come to the team? I have no idea how these things are connected. I don't know how this code looks like. And what if you want to push this to CI? How do you tell CI, hey, before building this, please build those applications? So let's say I want to build payment screen. Now, if you see this graph, we know that in order to build payment screen, we need to build payment service, and before we build payment service, we need to build util stripe. So the correct order would be util stripe, then payment service, and finally payment screen. But how do we know that? How do we know that they are connected in such a way? Just by looking into the code, we might see something like this. So payment service might have a checkout file, which imports our payment service. The thing on the right side shouldn't scare you. That's just TS alias path, just to make it shorter and not have a full path. And similarly, in payment service, we can have another file that imports from our util stripe. So it's already there in your code. You just have to read it. But of course, you don't want to do this every time you build application. It's annoying to create this code analyzer. That's where the monorepos come into play. They come with these functionalities pre-built that analyze your code and can come up with such dependencies. So this graph was actually generated by NX just by generating the libraries and linking them with imports. So this is automated. And once we have this automation, we can also have orchestrator that runs these processes in the correct order. And not only that, now that we know how things are connected and in which order they need to be invoked, we can also see how they depend on each other. So let's say we change the util stripe. Again, based on the graph, we can tell that only the payment service might have been affected. And if payment service might have been changed by util stripe, that means that potentially payment screen is changed, and then our application. And if we know that the application has been changed, maybe we should run our end-to-end tests. So just by making one single change, we see all this chain of changes that might have happened that we need to check. But we know what these changes are, so we don't have to check anything else. We know that all the other libraries and all the other projects could not have been changed. By the way, when we're talking about monorepos, the folders stay the same as what Raj was splitting, with a small difference that each folder is now a project, a library, or an application for you. So let's say we did this change. If we would run it, we would get something like this. So we run affected with the target build. You can see the first 4 that were listed. Those are just dependencies of the coffee app. So we take them from the cache because they were not changed. But then you can see the rest of them being built in the correct order. So util stripe, payment service, payment screen, and coffee app. And you might be thinking, but how do you know this? I mean, how do you know how these files were changed? We use a simple git diff to see, do we have any untracked files? Do we have some stage files? And finally, if we commit something to our local repository, to compare to our branch that we are trying to push to see what are the differences. And for CI, it's a bit tricky because your commit that you are pushing is the same as the top of the branch. So that would be just comparing commits to itself. So it wouldn't trigger any change. So maybe we want to then compare it with the previous commit, right? But for PRs, it doesn't really make sense because you want to include everything you did in that PR as a one chunk. So you want to compare all the way down to the branching point. Now, of course, if you're pushing to a single branch, not to a PR, it's simple, right? It's just last commit, or is it? Because last commit might have been broken, and you don't want to compare against that one because you would be swallowing that error. No, you want to go all the way down to the last successful commit. Figuring out the last successful commit might not be that simple. But don't worry, we can help you out because we created Circle CI orb and GitHub action that does exactly this. Uses the underlying APIs to find the last successful build on a given branch and gives this as an information to our affected function that will then use this as a base for comparison.
If you're watching a football game and there's a goal, and then there's instantly a replay of that, it would be weird if during the replay they would miss, right? That would be weird, right? I promise I'm going somewhere with this analogy. But the point is, we are used to watching an event, recording it as it happens, and then replaying those events exactly as they happened before. So instead of a goal, you can imagine a build. When you build your app, right, it might take a while eventually. Like Webpack will start pulling in all those files. It's going to pass them through some loaders. It's going to start bundling your app. And after some time, you'll end up with some generated JavaScript bundles in your dist folder and with some terminal output describing what happened during your task. Those are the only 2 outputs of the specific process that we run. So you can imagine if you run the exact same build a few hours later without changing the source code, it would generate the exact same terminal output and the exact same JavaScript bundles, right? So what is the point of doing all that work again if nothing will change? That's what the distributed caching system does. It's a central service that ensures that no computation is ever run unnecessarily twice across your whole company. So it does that by watching what commands and what tasks everybody's running across your across your organization or whoever's connected to it, including your CI. And it checks against which source code those commands are being run. And if it spots a task which will return the exact same outputs as a task that has been previously run, well, it's just going to give you back the previous results without you having to rerun that computation. So you can imagine some applications of this. Any commit that goes into your main branch, CI will try to run some tasks on it. So it might run build, test, it might run some end-to-end tests on it. So when you come into work in the morning, and you pull latest main, and you start work on that shiny new feature, and you try to build your app, well, you should be able to instantly just replay the build because it already happened on CI probably a few hours ago before you came into work. Another example can be pair programming, right? So let's say you're on a call with somebody, you do some changes, and you serve your app to test those changes, and it might take a while, right, because there's some new changes. But once they pass, when your colleague tries to serve it as well, because you're both working on the same branch, I mean, it might finish instantly for them, because why should they redo that build again? And that's what a centralized caching server can do. Another more advanced example is, let's say you're adding a recipes page to your app. So you made some changes, which results in that affected graph. So now your CI will start up, and it's going to start running some tests, right? So in this case, it's going to start running your lint tasks. Well, it might take a while, so those tasks might finish slowly, eventually, but then you get a failure, right? This is annoying. So you make a new commit to fix that failure. You push a new commit to your PR with a fix to that library, and it turns out the issue was just a forgotten let in there. That should have been a const. So your whole PR was broken, and now normally you would have to wait for all your tasks to get executed again, right? You push a PR, and almost until it's done, you get a test failure. So then you fix your test, and then you have to wait for all of your tasks, all of your builds to execute again on that PR. But in this case, when it comes to our lint tasks, well, because we just made that one-line change in my utility library, there's really no way it can affect the lint results of any of those libraries. Linting is mostly like file-based. There are a few exceptions, but we kind of know intuitively that just that one change can't really affect the lint results of those libraries. And the caching algorithms knows that as well, because it's aware of what tasks you're running. So when you push that second commit, it can just instantly pull the cached results from the first commit where it ran. And it's only going to do the necessary work for the second commit which you created. And the most important thing I want to say is, sorry, hold on a second. Hello?
Rareș, what are you doing?
Hi. Yeah. No, it's perfect. Yeah, I can talk now. I have time. Sorry. Yeah. Oh, okay. Okay, yeah.
Sorry, folks, for this.
Sorry, Miro. That was my niece. She's
Okay.
panicking about her math homework.
Okay.
Do you think we can help her out a bit now? Is
Okay.
this a good time?
Yeah, we have a minute or two.
We have
Yeah.
some time?
Yeah.
Okay, cool. She said she's going to send over the problem, so
Okay.
let's see if they come in. Okay, there you go, first one. Can you help her out?
Yeah, it's 101, right?
Oh, perfect, nice. If anybody wants to try and do this. 167 plus 51.
Oh, this is harder. It's 218, right?
Oh, awesome, good job. Okay, and I think...
Are we done? Oh, how many more of these?
Wait, let me check.
What?
Okay, wait.
Come on,
okay,
we don't have
we
time
have quite
for
a bit more.
We
I'm
don't
not
have
sure if
time
we
for
have...
that.
We don't have time, right?
No, man. Just tell her next time.
No, I think,
Or
can anybody
maybe you
help
can
us
help.
out? I mean, this seems like a lot of work for one person, but what if we split this up a bit? So can everybody try to either navigate to that URL on your phone or scan that QR code and enter your name, please? Well, let me see.
I heard there's an award for the one that solves most of these equations.
Well, let's see if it's going to work. So can anybody who, if it's working for you, can you raise your hand once you entered your nickname, if you see a web page? Okay, awesome. Thanks for doing this, by the way. You're really helping us. Unless, we don't want to be here for the next 5 hours. So, this is a game I made just for this talk. So I'm not saying I wrote too many tests for it, but I didn't write any tests for it. So, so I have no idea what's going to happen. If it doesn't work, I have a backup plan. Don't worry. So cool. Is everyone ready? Can you see it changing? Oh, cool. Look, people are doing it.
Oh, amazing.
Oh my
You're
God,
so
it's changing.
fast.
It's changing.
Wow, all the math geniuses in one room. Look at that.
Oh my God. Okay, let's see.
Let's see the stats.
Oh.
Lean Soldier leading.
Lean Soldier is winning. Come on, just a few more. Lean Soldier. Oh my God, that's such an... Come on, just a few more, I guess. 3 more, 5 more. 2 more.
Will JSL catch up?
2 more, 1 more. Is that finished? Lean Soldier. Who's Lean Soldier? Nice.
Can you come over?
Well, after. So we have a cup for you, so you can enjoy skiing. You can enjoy your coffee while skiing. Good job.
Thank you so much. You saved us a lot of time.
So, well, let me see if I can go back to this. Right. So you saw, even with Miro's impressive math skills, there's only so much a single machine can do. Like eventually you're going to
Thank you for calling me machine. Appreciate it.
Silicon or carbon based. Eventually, you're going to reach the physical limits of how much a single brain or computer can do. So you will need to distribute your work so that it can scale. Like you helped us just do it right now. Because you saw how we just solved 100 math exercises in probably less than a minute. So how can we distribute the tasks in our workspace? Well, when you submit a pull request, a CI system, usually such as GitHub Actions, will pick up your changes, and it's going to create these VMs, right? These machines with some resources that can run your tasks. And it might create one or multiple of them. So you might configure your CI YAML file to just run all of your tasks serially, one after another. Right? That's a simple way to do it, but you can see how that's going to get slow, right? Very, very soon as your workspace grows. If you have a powerful machine with a few more cores, you can try to parallelize them a bit, right? So that's going to speed them up. But eventually, as your workspace is growing, you are going to add more and more tasks to that, and you are going to end up back to square one. So you do need a way, you do need a strategy for distributing your tasks across multiple machines that you can easily add more or less so that you can be ready for scaling. It doesn't have to be right now, but you can be ready. So how can you distribute? Well, one way is, let's say I can do all my build tasks on one machine and all my lint tasks on another CI agent, right? That's going to speed things up a bit, right? Instead of those lint tasks being over there, they're now finishing as quickly as the build. But that's a problem, because the lint tasks are very short, they might finish very quickly, so that agent will idle away when it could actually be helping that first build agent pick up some work. So then we can say, because the build tasks take so long, what if we just move half of them to the second agent? They're a bit more balanced now, but then we have another problem. Our end-to-end tests depend on the build of my app, so they can serve it and test it. The build of my app depends on the build of these two other libraries, which depend on the build of these other utility libraries. In that case, we will have to run all those tasks on the same agent so that they have access to each other's outputs on that agent's file system. We just saw how a distributed remote caching service can help you avoid unnecessary computation in your workspace. What if we use that same service and we let it handle orchestration and distribution for us? So instead of manually configuring what each agent should run, what if we tell them just to listen from that central service? They're just polling, or they're just receiving events from it. So the first agent might receive, hey, some lint tasks and maybe a build. The second agent might get some builds and maybe some tests. The third agent might get some tests and maybe some lint tasks. Our orchestration service knows from historical runs how long on average your tasks kind of take. So it's going to be able to distribute them optimally whenever it sees them again, depending on how many agents you have. And when the time comes, your end-to-end tests will start running. And check this out. This agent is running some tests and some lint tasks. But this end-to-end task that just came in needs some build artifacts to serve. Those build artifacts have actually been built on that second agent on that other machine over there. Turns out that using distributed caching, it doesn't only help you save computation and makes you run tasks faster, you can also use it to move computations between different machines so that you are suddenly not limited anymore about how tasks depend on one another. So when these end-to-end tests have to run, they can just pull the build results from the shared cache, even if it happened on another agent. So they work really well together. So now, we have this dial. And if our CI gets too slow, we can just dial it up and add a few more agents. If it gets too expensive because we're now running all these machines, we can dial it down a bit, right, until we get more funding. And all the tasks will get instantly rebalanced again. So that's why we split up our graph into all these tiny tasks, right? For example, our end-to-end tests, instead of serving the app each time, we decoupled it from the build, and we're telling it, hey, just run the build first, and then serve whatever the build gives you. The more granular your graph of tasks are, and the more you tell the build tools about how they depend on each other, the better decisions that they can make around what can be cached and how things can be distributed across machines.
Okay. But you might be thinking, okay, come on, but how slow can it be? I mean, you heard this probably a lot of times that someone says, my builds are fast enough. I even heard it today. I don't need monorepos. My builds are fast enough. I'm going to tell you one very sad story. That's why I choose this sad waiting Pablo as a fitting picture. I was talking to a friend who is working on a front-end application in the biggest international organization that you all know of, but I won't mention. And he was mentioning they want to maybe switch to use NX monorepos and was wondering how much they can save time. And I was like, okay, how long does your build take? And he was like, well, I'm not sure. I was like, what do you mean you don't know? Like, is it 1 minute, 10 minutes, 15 minutes? Like, I would have to check, but I would say a bit over half an hour. I was like, what? No, I don't think build plus lend plus test, just build. Yeah, just build, just compilation. Like, how do you work with that? Like, how do you work during the day? How do you compile it? Are you waiting every time half an hour? Oh, no, we don't wait. We just run it at the end of the day or early in the morning when we come if we forgot the last day. Like, are you not? So you don't test during the day? No, because we can't wait for the build. So we just kind of run on what was built the last day and hope everything works out. So this might have sounded like an extreme, but we actually heard a bunch of these stories. We know a client that have end-to-end tests that run longer than 24 hours, so they can't really run it as a nightly build. They can run it as bi-nightly at best. But maybe you don't care about time. Maybe you're fine with waiting. Maybe you're fine with company wasting time on that and money, and also you don't care if your CI is too expensive. But maybe you care about environment, and using monorepos is good for the environment because it saves your CPU and thus saving the energy. So let's recap. You heard today, or you learned today, hopefully, that splitting apps is important because by making all these things granular, you can really focus on them separately in isolation, and you're saving times because you're only checking the stuff that you actually changed. And when using affected, you can actually know what things have been changed or possibly been changed. So we can never guarantee that all of these applications that were marked in a graph were actually changed or actually affected, but we can tell that all the rest of them were for sure not affected. So by doing this, you saved a lot of time of skipping running builds and all the other processes on stuff that couldn't have been changed. And finally, you should share cache, because by sharing cache, first of all, with yourself on your local machine, then with your colleagues and with CI, you save time and you save money and you save frustration. Maybe you save a couple of coffees a day as well. And when the work just becomes too much, because it happens occasionally that you have to update your packages and then suddenly everything is affected. In this case, it's good to distribute work across multiple machines to just narrow this window. But don't worry. We're not trying to cut down on your coffee breaks. We like coffee breaks, and we think that each one of you deserves their coffee break or tea break or whatever kind of break you want to make to be as long as you want it and to be whenever you want it. We just don't want your Webpack, your Jest, your ESLint, or any other tooling that you're using to dictate when and how long your coffee should be. Thank you for listening. Enjoy the rest of the conference, and if you're going to ski slopes, have a nice time.